Let's further recording. Let me just go back and review. What we're doing is just reviewing this problem. First term, first item, second, third. We're down to the fourth step here. And the fourth step, again, once we have the second derivative, is to, and again, I can't hear you because of the fan. Okay. Of what? Yeah, it's actually of one less than what you're working on. Okay, so it's the critical numbers of the first derivative, which happen to be the zeros of what? Of what you're working on. Okay, good. Second derivative. In other words, we set the second derivative equal to 0. Now, what do the zeros of the second derivative tell us? Thank you. Possible inflection points. And inflection points tell us changes in what? Concavity, yeah. Concavity on or of the first of the function. Okay. So the second derivative shows change in concavity. Now remember, a lot of what we're doing in problems like this, we really can look at the graph to come up with answers. Does this function have any extremity or any extreme points? Look at the graph. Does it go up and then down? Sure, it has one. But we need to get beyond just seeing if there is one. We want to know where it is. And the only way to get to an exact answer is analytically. And this is the analytical approach that we're talking about. Visually, on the graph, we can see a lot of the information we want, but we can't pinpoint exact values. Why are those important? Well, a lot of times those exact values are then used later on in the problem. And if I round the answer to 3 decimal places, isn't that good enough? I mean, money is only rounded to 2 decimal places, so if I round to 3, but what if that value that you round to 3 decimal places is going to be squared or cubed or some other power applied to it or some square root? And that value is what you're going to report to your CEO as to whether or not this function, this model that you've developed, is going to give the company a profit or a loss. A few pennies here and there don't make a whole lot of difference to us, but when they get multiplied and raised to powers and evaluated in many more other ways, they can become billions of dollars. I'm sure some of you have heard about ways of scamming. You just kind of skim off the pennies every now and then. And after you do that with a whole bank's account, you got $1 million after a while. And so if you do that unintentionally because you rounded the numbers and didn't think to always put in exact values, you could be in trouble. Okay? And I don't want to hear your names in the newspaper in that way. Okay? Positive ways, yes, but not in that way. So it's important that we go through and understand this so we get exact values so we can use those exact values in our calculations. Well, another thing of importance to us is this thing called points of inflection. Now, the inflection points, and that's about as much as we need to know at this point. The inflection point, I think we've talked about this maybe, talked around about it. The inflection point is where the concavity changes. And I think we talked about that. We've identified it graphically. But we need to, again, know how to develop these or define these with exact values. So let's look then further here. If the graph of a continuous function has a tangent line at a point where its concavity changes from upward to downward, from concave up to concave down or vice versa, the point where concavity changes is known as the point of inflection. Properties of the points of inflection. If this is a point of inflection, C is the input, F of C is the output, then the second derivative at that point is 0 or it doesn't exist. Keep that in mind. Or it doesn't exist. We can always have that possibility. That's kind of a formal definition of what we've been talking around about. Second derivative test. If I know that I have some extrema, so from the first derivative, I found my critical numbers of my function and I found my zeros of the first derivative, then if I put that value where that zero, that critical number occurs, and the second derivative is positive, remember positive means that it's concave up. If it's concave up, it has a minimum. If it's a second derivative value, when you put that critical number in from the function is negative, you know it's concave down, you know you have a maximum. If it is equal to 0, we don't know anything. We've got to investigate it further. The inflection point is somewhere between where it's concave up and where it's concave down. So somewhere in there would be our critical number of a function. So let's look at finding the points of inflection. The points of inflection come from what? First derivative or second derivative? So in order to get to the second derivative, we have to first do the first derivative. So there's no way around this. So we're going to determine the first derivative of this function. Now, how you go about finding this first derivative is up to you. I can think of a couple of ways I could do this. One might be to expand the cube of that binomial, multiply this out, and then multiply through by x. Giving myself just a degree 4 polynomial function. Now, if you like to, cube a binomial and do that, you have the choice. If you decide on some function you don't want to do that, then another one we could use is the power rule. And then we'd have to use on this factor, this is simple enough, but we would have to use the chain rule. So I'm going to do the second one because that's a good practice for our derivative work. Again, if you want to multiply that out and then get to it, that's fine too. So we've got the first factor times the derivative with respect to x of the second factor plus the second factor times the derivative with respect to x of the first factor. Let me just digress just a little bit. What does that mean? Say it again, Aaron. Yeah, oh wait. What are you oh waiting about? What do you see there? Yeah. Unfortunately, I had more than one person write stuff like this for the last quiz. When we have this notation, this is, as Aaron was trying to say, it is x times the derivative of y with respect to x. Take that and multiply it to this. Why? Because that y represents a function. I don't know what function it is, but whoever wrote this thinks that there's another function sitting out there called y equals, because that's the way it's written. What we should write is what we have over here. I want the derivative of this output with respect to x. So if you're guilty of this, if you did this on the quiz, you're going to see some marks, so just be prepared. This is improper, and it's like you're being so picky. It's not so picky if I don't know a language, but I use some terms because I memorized some phrases, but I don't have a clue what I'm saying. Do you realize you can get into big trouble for that too? It's the same thing here. This is a language. And if you don't understand the language, you don't understand the notation, you really don't understand the mathematics behind it. We're talking about some value, some function, such as, over here that you're taking the derivative of, and then you're multiplying it times that. Okay, well, just a little bit of that. So I've got x times, now I've got the derivative of a cube of another function, so I've got to use the chain rule. Some of you missed this on the quiz. And then I've got to take the derivative with respect to that inside function. Again, some of you are not writing out all the derivatives. Will you hear from me on that? Yeah, you will. You will. Plus x minus 4 to the third power times the derivative of x with respect to itself, and it's just 1. So let's see, I've got x. Actually, we can make that 3x while we're at it. 3x, x minus 4 quantity squared. This is going to be times 1. Plus x minus 4 quantity cubed. So, here again now, what are we going for? Are we looking for extrema? Doesn't say, okay? You can go ahead and do that if you wish, but it's not asking for extrema. If we wanted extrema, we would have to stop and take the zeros of this. But we're looking for points of inflection, and that comes from the second derivative. So, how you finish this up is up to you. You might say, well, I'd like to factor out an x minus 4 quantity squared, and that gives me 3x plus x minus 4. Or simply x minus 4 quantity squared times 4x minus 4. That may be where you want to go with that. You may want to leave it like this and work it from there. I think I'm going to even do one more step and make it 4 times the quantity. Let me put that 4 out in front. 4 times the quantity, because I'm taking a 4 out of that last one there. Now I need to find the second derivative. It's just taking the derivative of the, if you want, go ahead and expand it, make it into a polynomial of degree 3, if you wish. But I think I'm going to opt for the product rule again. So I have the first factor times the derivative with respect to x of the second factor, plus the second factor times the derivative with respect to x of the first factor. And I guess I need, I'm going to take that out of there. Don't really need to have that. And then I have 4 times that whole thing. Taking the 4 out in front of the whole product of these, as if there were brackets there. Okay, so let's see. X minus 4, quantity squared, times 1, plus x minus 1. And now I've got the chain rule I'm going to have to use over here. So let's see, that's going to be 2 times x minus 4 times the derivative with respect to x of x minus 4. When I graded your quizzes, I noticed that, you really, a lot of you have a lot of good stuff going on, but because you don't put in enough brackets and you don't follow through with the negatives and you don't tell yourself what derivatives you're taking, you're dropping those and you're dropping points along the way too. Okay, so I've got 4, and let's see, this is x minus 4 quantity squared, plus, let's see, this will be 2 times x minus 1 times x minus 4 times 1. I'm going to opt not to put that in. And now that I have now that I have that done, I guess I could factor in an x minus 4, couldn't I? You know, it depends on how far you want to take this, but what's my next big step going to be? What's the next big step? Set it equal to 0. Yeah, exactly. So let's see here. Let's see, 2x and x should be 3x. Negative 4 minus 2 is negative 6. So it looks like I can factor a 2 out of here. So I should get 8x minus 4, x minus 2. There's no y's in there. Did I have a... Yeah, sorry about that. As the day wears on, my handwriting gets worse, so you see the worst of it here. Anything else, though, that you need clarifying on? Okay, so we'll do that. We'll set it equal to 0. So I have 8x minus 4, x minus 2 equal to 0. And we have to say possible inflection points. Possible at x equals 4 and at x equals 2. Now, how do we know for sure that those, in fact, are going to be in points of inflection? Oh, they're points of inflection only if what happens? What switches? Concavities. Okay, so here we go. The next step then to test is we need to test what happens on either side of 4 and 2. So we can set up a sign chart. So we look at the intervals. And let's see, if this is 2, there's 4. We look at a test value. And so I'm going to test x equals, now I didn't look at the first derivative. This could be a little dangerous because I don't know. I don't know that maybe I have a critical number at 0. But you know what? I'm going to try it anyways, because if 0 fits into the second derivative and makes it positive, then I know that I've got a minimum at that. I'm just looking at where concavity changes. So it doesn't really make much difference. I'll choose a 3 here, and I'll choose a 5 over there. Let's test the second derivative. So let's see. Second derivative, I'm going to pick up my 8 times x minus 4 times x minus 2. So this would be 8 times 0 minus 4 times 0 minus 2. So that's 8 times negative 4 times negative 2, second derivative. Positive or negative? Positive. My conclusion is that the f of x is concave up, looking like that. Try my next one. So that's 8 times negative 1 times 1, my second derivative. Negative. Okay. So my conclusion is that the function is concave down. What do you think about at x equals 2? Is that a point of inflection? Did concavity change? Yes. Okay. So we can say, therefore, f of x has a point of inflection at x equals 2. Well, what about at x equals 4? Now, I've got a problem with this. Do you see the problem? Oops, I chose 4, didn't I? Why did I choose 4? I don't know. I'm going to say that's a big problem because that turns out to be 0, and I don't need that. Okay, so let's see. 8 times 1 times 3. Second derivative is positive. So f of x is concave up. So what do you think at x equals 4? Inflection point? Okay. Okay, that's the type of work then that we need to go through. We're asked to find inflection points. Okay. Let's go on. I think we'll skip that. You guys can do that on your own, can't you? Got enough examples? Okay. Sketch. Have we done this one? Good. Let's do it. Sketch the graph. Soccer team's going to go off and get a victory. Okay. Yes, you want those pieces? Okay. While everyone's working, go ahead and keep working on that. I counted anything above the, if you had extra credit, anything above the points that came, they could get an A plus on this, were counted as extra points on your extra points on your quiz average. Okay. Let's see. Choose. Okay. Okay, let's see. Okay, so this curve, piece by piece, you pick up every little piece, you know what you're doing. What I want you to do is, you got to work on this problem again later on. Okay, use the graph shown. Find intervals on which the first derivative is positive. Am I asking you for any different mathematical thinking than the last one? No, I'm not. I'll give you a hint. That's 2, and that's 3, and that's -1. I'll put that as a 0. When you tell me intervals, you're going to tell me intervals of the input variable or the output variable. Okay, so you've got a task. Go ahead and work on it.
Just looking at it makes 15 absolute sense. Because I was thinking,
Okay, Kevin, you have part A. The first derivative is positive. What intervals? from 0 to 2. Okay? Any others from anybody else? Okay, visualize the tangent lines. Okay. The first derivative is negative. Intervals. Katie, again?
Negative 1 to 0.
Now, you have to imagine this continues on. It's not stopping. Okay, negative infinity to
0.
0
2 to
and 2 to infinity. Yeah, well, I have to remember that these are not limited to the screen we see. Okay. The first derivative is, now, you have to be careful here. The first derivative is increasing. Did you think that A and C were saying the same things? They're similar, yes, but they're not saying the same thing. When you looked at the first derivative as positive, you were considering what happens on this is f of x. What's happening on f of x? When I say the first derivative is increasing, I'm now having to consider what's happening on the first derivative. So where is the first derivative increasing? Is the first derivative increasing here? The first derivative is a tangent, right? So is the tangent, and we're talking about slope of the tangent, is the slope of the tangent increasing along here? It's negative, right? And eventually the slope becomes 0. Is the first derivative increasing? Is negative 10? It's getting closer to 0. Yeah, it kind of tricks you with that. But negative 10 is less than 0. So if I'm going from, let's say, negative 10 to negative 5 to negative 2 to negative 1 to 0, is the first derivative increasing? Yeah. Okay. Now, let's continue on. Over here, is the first derivative increasing when it goes from 0? But then think about it. What happens at this point? The first derivative is increasing, then all of a sudden, let's say right here, the tangent of the slope of the tangent is, let's say, 5. What happens as I move around this curve? Then it becomes decreasing, doesn't it? Where does it change? Katie?
I have a question.
Yes, yes, you would. Yes, because what we're doing, we're analyzing the first derivative. Now, let's do it this way. I'm going to change colors here. Would you agree that at 2, the first derivative is 0? So if I put in green the value of the first derivative, I've got a point right there. Where else do I have a point on the input axis for the derivative? At 0. Now, is the first derivative positive or negative here? Are the slopes positive or negative? Negative. So this is actually down here, isn't it? What about here? Positive. The slopes are positive, so I need to be above the input axis here. Something like this. And then what happens here with the slopes? They're negative again, aren't they? That's a bad looking graph. Okay, but you get the point of it? This is going up and then coming. Let me see if I can take one of those away. Oh, take the whole thing away. Okay. So I've got something like this. Now where do you think this derivative is going to peak? Have an extrema. I think so too. Now, how far up it goes, I don't know, but it's going to peak there. Why would you say at 1? What else do you think happens at 1? change in concavity known as the inflection point. Yeah, so I'm thinking it's going to peak right about there and then come down here, and then it continues on. So the first derivative is increasing where? From negative infinity to 1, it's decreasing where? From 1 to... Isn't that an interesting way to look at that graph? It kind of plays with your mind a little bit. Now, let's see here. Would you take your inspires? And we're going to actually put this function. I didn't tell you what the function was. I'm going to tell you now. Okay? I want you to look at this. And the function is, here we go. Well, I'm going to tell you because evidently something is not. Okay, be that way. I'll tell you, and you guys can work ahead, and I'll work on mine up here. Oops, now it wants to be good. Okay. Okay, I'm going to put in a graph, and it is negative 1/2 x squared times x minus 3. Now you might need to put a multiplication in here, so I'm going to just go ahead and do that anyway. We should see the graph that I'm showing you there. Whoops, what doesn't it like? Yeah, it didn't like it down there. Okay. The window, let's just go ahead and do a window so we have that. Let's see, the window is negative 3 to 4, scale 1, and negative 3 to 3, scale 1. Okay, so there's the curve that I gave you. I can have you compute or determine the derivative, but let me just kind of give it to you here. Well, no, let's do it this way. Go to the template, so control on this model, control on the multiplication. On the black one, you just got your own key, the template key, and let's do the derivative with respect to x of what? F1 of x, right? We'll let it do all the work for us. Okay, and I'm going to change the attributes. I'm going to change mine to be we'll do that. Okay, there's my derivative. Is that what we determined it to be? Okay, let's do one more thing. Let's analyze the second derivative. Now, if you analyze the second derivative, which of these curves are we going to be going through and talking about? So any place on this derivative you think might be of interest on the second derivative? Again? Yeah. So what's going to happen on the second derivative at this point? It'd be a 0. I should have a point right down here. And to the what's that direction to you? To the left of, right of that? Okay, to the right of that, are we going to have second derivative values above or below the input? Why would it be above? Did you say above? Oh, you said below. I'm sorry. Yeah, below, because if you think about tangents to this, they'd be negative slopes. Yeah. So you can analyze those a lot. Now, what happens? Let's see. The inflection point should be right there at 1. Let's see if that's actually true. I'm going to go over here to menu. I'm going to analyze. I'm going to get a maximum of this curve, and right there it is, right where I thought it was, which would correspond to an inflection point right down here. Okay? Well, be aware that those are some fun ones, but they're also ones that you can really, I can test you on whether or not you truly understand. Okay, we've got 15 minutes. I'm really anxious to get to the next few problems. So let's move on. Consider a college student who works from 7 p.m. to 11 p.m., called the second shift, for those of you who know anything about factory times here, assembling mechanical components. The number n of components assembled after T hours is given by. Who thought up this equation? Who says that's what it is? Cole, did you say that? Sure, somebody who's looking at data. You know, I keep bringing you back to that because we get this idea that somehow mathematics is only for those people who sit in a math class, when in fact they're out there considering how many components can be assembled by a college student on second shift after T hours of being on board there. At what time is the student assembling components at the greatest rate? At what time? What do you think you need to determine? The derivative. And when you're considering the derivative, you want to know, now the rate is, you know, how fast is the, at what rate, excuse me, is are the components being assembled, but we want to know what the greatest rate is. So are we just looking at the first derivative? We're actually looking at the second derivative. We want to know where's the maximum on the rate function. How fast are they assembling these? But we don't want to know that. We want to know what's the greatest rate. So we need to actually look at the second derivative. So we need to find the first derivative with respect to t. Make sure you've got that. Go ahead and work on it. I'm going to do my work up here. You know, you can stop at any point and take the second derivative. But I like to go, you know, make it as clean as possible. And so I'm going to continue working on this, hoping I don't make any errors along the way. Is that truly as nice as it is? By golly, it is. See how nice it is to go ahead and finish it up? Those 40t cubes cancel out. Because of the, okay. So this is going to tell me the rate at which components are assembled. I don't want that, do I? This is kind of getting us into that next section called optimization. We want to optimize this rate. And so now I need to look at the second derivative. What might make this work a little easier? Anyone do something different to start this? I'll tell you, if I squared that binomial, it might have made it a little easier. Did anyone try that? You might want to. Keep that tucked away as something that might have helped. Oops, can't do that yet. I did a couple of things together in this step, I have to admit. For those of you who might go back and look at this, I took the derivative of this as 2 times t, and I took the 2 times 2 and made it 4. That may be too confusing. Let me go ahead and not be so anxious here. Put the 2 there and the 2t here. When I get this all done, what am I really wanting to find out? You know, it's kind of like, I get this derivative, so what? What am I trying to find? What am I trying to do? Trying to maximize it. Yeah, and I'm going to maximize it by looking at what? I'm sorry, what was that again? Yeah. So, you know, at some point I'm going to set this equal to 0. Now, I can decide where I want to do this, when I want to do this. You know, I'm going to factor out a 4t squared and 160, and that's going to leave me with a 4 plus t squared from the first one, minus 4t squared. You know, I'm just as likely as you are to drop some terms here. So I'm going to have to make sure that I do a check on it. Take that out. I have 1 left. Take the 160 out, and then I've got the 2 times 2 is 4. I have the t squared. I took that out. I think I've got that. I know someone's watching. I can take one of those away from here. So I have 160 times 4 plus t squared minus 4t squared divided by 4 plus t squared cubed. You know, you got to check this stuff. What happened to the t? T times t is t squared. Okay, so I'm going to check mine, make sure, see if I can find it here. By golly, it's right. According to my work there. I'm not worried about that I should be sure it's right, but I'm not worried about it because when I set it equal to 0, What's the only portion of the fraction that makes any difference? The numerator. So I'm going to say 0 equals 160 times this. And that gives me that 4 minus 3t squared is the only 0 I could have. So t would be, let's see, square root of negative 4 divided by negative 3, or 2 divided by the square root of 3. I should have a plus or minus in there, but do I really need it? You take the square root, you got to be careful. Why would I not need to have a minus in here? What's t stand for? Yeah, the negative, t stands for hours, so I'd have negative hours. Okay, so would you walk in someplace and say, well, I'll tell you what, your greatest rate of assembling is going to come 2 divided by the square root of 3 hours after the first, no, you wouldn't do that. Okay, you'd probably take care of an approximation, and I've got approximately 1.15 hours after the student starts working, you're going to get the greatest rate. Now, are they going to be assembling the most at that time? Well, if they're working the fastest, now the greatest rate means that the rate at which they get it done is increasing over time. And so that is something that we'd have at the greatest rate. They're not assembling that many per hour. And the number that increases per hour isn't going up by 1.15, but the rate at which they're assembling is going up. The rate at which is going up that much. Okay. These are interesting problems. And we have to, first of all, understand what it is we're trying to find. And this one, let's go back, because this was an interesting problem. It says, not that. Let's go back to where we were. The problem says something else. There we go. There we go. At what time is the students assembling components at the greatest rate? Okay. So yeah, at 8:15. They're assembling them the fastest that they will ever assemble in the whole. Now, how do we know it's a maximum? We didn't really test that, did we? That could be just an extrema. That could be maybe the slowest rate. We have to go in there and kind of check around a little bit, but we'll leave that problem for now. Okay, the next, and again, what we're heading toward is that section of optimization, the one where all we do is look at things like this. Before we get going there, and I got some quizzes for you, we have this thing called the point of diminishing returns. Have you heard of that in the business? What do you know about it, Cole? Make your business profs proud. What do you know about it?
The point at which
you're not going to read off the screen, are you? Goes down. Okay, output per worker goes down. He applied something a little different. Is that consistent with what we have on the screen about dollar amounts? In what class did you learn about that? Econ 1. Okay. So Econ 1 maybe is a better connection with this class than Econ 2, as I always thought. Okay, the point at which each dollar begins to return less. Now, when what Cole said, it would be the point at which each worker produces less, begins to produce less. Is that what you're saying?
Well, it's like if you add more workers on the one task, like the workers. It's kind of like a competition space, so they do less work per worker.
So your input would be the number of workers, and your output would be what? Output? I mean, product output? Okay, so as you put more workers on, does that mean you're going to get less output? So in this case, we're not going to get less dollars, and if I apply that to what Cole said, we wouldn't get less product from those workers. We just wouldn't get the increase on the amount of product as we were seeing back here. Now, let's look at that. If I draw a tangent here, and I continue to draw tangents along here, the tangents are getting steeper, which means that the rate is greater. And then all of a sudden at this point, for one thing, what happens to the tangent lines? Ryan? And they decrease, but what else? I can't hear you. That's true, but what else? That's true, but what else? There's something else that happens. If I'm going to draw a tangent line along this curve, let's see if I can get that. Where's my magic marker thing? If I'm going to draw a tangent line, there we go. And I'm going to pick up that line and I place it here, and then I place it up here. What happened to that tangent line? Because there's a point where I'd have the same slope, but what happens to this tangent line from going here to here? It's on opposite sides of the graph. Yeah. Did you notice that? Here's below the curve. Where do you suppose it switches? And what's our name for inflection point now? Point of diminishing returns. Because if I take this and I begin to work it around this curve, I am getting slopes that are now beginning to level off. And so I'm still increasing in my output, my product output, or my dollars or whatever, but I'm not getting as much benefit from each additional worker or from each investment dollar that I put in. For the point of diminishing returns. Okay, we'll take care of that. I've got your quizzes, so sorry to keep you 2 or 3 minutes late, but you will, some of you want to see these. What I did was I took the extra credit and I applied it to this course, so that gave you an A+ on classes. In other A+. And so I applied it to points. Listen carefully, you're going to want to know this. I applied it to points above. I applied it to a column by a spreadsheet that says extra credit. So I'm going to add up all the points I have for quizzes. But I'll divide by one less column, the extra credit column. Down there, please. Ella? I got all of mine. Daily. Angie. 7. Brian? I get it. It's like I either had A's or I had T's. Philip. Down to Philip. Alyssa. Down to Alyssa. Aaron. Charlie. Way down. There you go. I thought you said that. Remember that there's a special buzzer that's going to go off. You put everything in place. Okay, see you all Thursday.